Hello, this is David Lonigan. This is my full video from my big data final project about the Cascading Java API. My final project concentrates on using the Cascading Java API as a replacement for the Hadoop Java API. The Cascading API implements a higher level of abstraction than the Hadoop API. Its abstraction model includes database operations that under Hadoop must be built up from more primitive operations. In my project, I use cascading API calls that perform database projection, selection and renaming of columns, and database aggregation, grouping like tuples and performing an operation on them like counting or summing. Cascading also provides operations for joining different data streams not covered in this project. In my code project, I use the each and fields classes and the identity function to perform projection. I use the group by fields in every classes to perform aggregation. I believe in the context of this course and helping my colleagues learn about this topic. The best way to accomplish this task is to rewrite some homework solutions where we use the Hadoop Java API and instead use the Cascading Java API. This way everyone is already familiar with the problem and the input data, so I can concentrate on the API differences. Before that point, I explain the cascading build and execution environment. I break my final project into three problems. One, build and run the cascading word count demo. If you can't run a product's hello world sample, also known as word count, nothing else is going to work. Two, I run our course's word count and do a column swap on the output. This is assignment 6, problems 1 and 3. Not all word counts are created equal, and our Bible data text won't work on the cascading demo without code changes. 3, in the key part of this final project, I rewrite the non-graphical version of the patent citation, inverted counter, and non-graphical histogram using the Cascading API, which is from assignment 7, problem 1. This is an original work of programming, but I did start out with the skeleton code from the demo. Installation of the Cascading SDK is straightforward and is simply unpacking a tar file. I chose to put it in user lib. You can see that I put the tar command on this slide here. Warning, I did experience Java security errors when writing to HDFS. This was when Cascading was writing some intermediate files. In order to get around this issue, I made an HDFS configuration change in HDFS site.xml. I changed dfs.permissions to false. Demo comes with Gradle builds, but I really want to know what was going on, so I created shell scripts from the builds files. I created a shell script to set environment variables. This gets used in compilation. I created a compile script and a script to create the jar file. Notice that the jar file takes two elements, the class that was compiled and a library that contains the cascading libraries and any third parties the cascading libraries depend on. In this compilation of Cascade Histogram 2.java, the Cascade class that I wrote is included in the jar file, but also all the supporting cascading jars and a third party that they depend on is included in the jar file too, and this entire jar file will be executed. I created a script for running cascading Java API applications on Hadoop, but the script is the same as running any kind of Java application on Hadoop. You may remember from assignment 7, problem 1, the patent citation input data file. It consists of two columns, patents that are citing and patents that are being cited. And the top of the columns have column names. Note that I had to remove the double quotes from the column name citing and cited, or Cascading would interpret the double quote as being part of the column name. This is the actual output of running the Cascading Java API application. It matches the Hadoop Java exactly, except for the number of patents that are referenced once at 921,127. This is one less than the Hadoop Java API. However, it turns out that there was a bug in the Hadoop Java API program inverted counter, where the column header was being counted as a path and being referred. So the cascading Java API solution is actually correct. So this is the correct answers. Now I'm going to analyze some of the code for the full version of the cascading Java API to do the inverted counter and non-graphical histogram. In this application, I'm actually combining cascading API calls and Hadoop API calls. That's because if you don't use generic options parser in your application, then the Hadoop jar command won't work correctly under certain circumstances. If you pass out options, the options won't be interpreted correctly. So this is why I use Java Hadoop API calls, but just at the beginning of the program to do the parsing correctly. After the bottom of this slide, everything else is completely in the cascading API. In the cascading demos, they don't do this. They don't put any Hadoop API code because cascading can run on Hadoop or not on Hadoop. But in my applications, I'm running it all on Hadoop, so I wanted this change. Again, the key is the generic options parser. This program is going to be chaining two different aggregations. If we look where I have the mouse here, first we have input and output sources. Cascading uses a plumbing analogy where you have sources and sinks and data is flowing through pipes like water through pipes. And at various places in the pipes you can operate on the data and transform it. You can split pipes and recombine them. In the bottom 4 or 5 lines, we're doing an aggregation. First, we're projecting just the cited field because that's the only field we're interested in aggregating. And then the group by in every classes are being used to aggregate cited. And on the aggregation, on each aggregate group is being applied the function count. In the Hadoop Java API, this is a full Hadoop program. But here it can be done in just a few lines. And this is the first part of the chain. If you remember from that assignment, we're now going to count the number of counts and be able to say how many patents were referred to once and how many patents were referred to twice, etc. And so we're going to do a second aggregation, which is what we're showing here. First, though, the first aggregation produced a field or a column name called count. But since we're going to do a second aggregation, that will also try to produce a field or column name called count, and they would conflict with each other. So I'm going to use a projection to rename the first count field to site count. And that's done here with the identity class, which is actually used as a function. So each class applies a function to each tuple in the data stream, a tuple being another name for a row, and to be able to transfer it. In this case, we're using identity, which returns just what it receives, to only return to first of all rename the field and also only return the site count because that's what we'll be aggregating on. The last few lines here are the second aggregation, where we group by site count, which is the count we produce from the first aggregation, and then we count those groups in the same way. That's the full aggregation. Finally, again, in the metaphor of the plumbing metaphor, we have to connect all the pipes to the source of the data, where the data is going to, the sink. And put it all together with the operations that are going to happen on the data stream. You see on this line here, the code is writing a dot file. And this is like an execution plan or a data flow plan that shows how cascading has connected all the various pipes together to produce the answer. We'll take a look at an example of a dot file shortly. Cascading is running Hadoop jobs, and I took a few lines from the output to show it first starting one Hadoop job and then starting another Hadoop jobs. And again, though, those are the underlying implementation of the aggregation and counts that we were doing under the Cascading API. Here's an example now of the dot file, which is showing the data flow. And if you follow these arrows, you can actually follow it from the source of the data, HDFS, onto intermediate files, and then finally onto the ultimate destination for the solution, which is also on HDFS. I did want to comment one more thing about the input. Notice that the input here which is the source, uses class text delimited, and this class is using a comma delimiter. So this corresponds to the input of the patent citation data. There are different classes for different kinds of data. There's a different class example used for unstructured data for our word count when we were using the Bible text to do word count. I don't include that code here, but in my report, I also include the modifications for word count to get it to work with unstructured data using the Cascading Java API. Conclusions. The Cascading Java API is clearly more powerful and expressive than the Hadoop Java API. The reduction in code size for Hadoop job chaining operations is significant. Also, the code is linearly in one place. No need to jump around. Also, Cascading automatically took care of creating and deleting intermediate files. The Cascading suite of software is quite large, and I only touch on one aspect. This technology would have a long learning curve for complete mastery.